Let's have a look at the a different way of accessing the I/O pins. And here's a schematic of the Uno, and this is the microcontroller, the ATMEGA 328 that you actually program. This one over here is used for the USB to serial conversion. We're not interested in that one. But I want to show you something here on this microcontroller. There are 20 odd pins that come out to these connectors here. These are the connectors that are around the outside edge of your PCB, your circuit board of the Arduino. These would be the analog pins here along the lower right hand side, and these two connectors here and here are the two connectors on the upper part of the circuit board. If you're holding it in the way that the Arduino, the lettering on it is visible, is legible. And you notice how they've grouped these I/O pins here in groups like this, these three different groups. And you notice that they're lettered the same way. This is PD 0 through 7, this is PC 0 through 5, and this is PB 0 through 5. And why are they organized like this? If you look at this one here is 8 I/O pins together in a group. This one is 6, and so is this one. Well, there's a reason. And these are what's called the I/O ports, and they're organized in terms of the width of a bit, or the width of a byte, 8 bits wide. And the reason for that is if we look at the ATMEGA block diagram here for the microcontroller. So this is the CPU, the part that interprets the instructions and does what the instructions tell it to do. This here that runs throughout the whole system is the data bus, and it's 8 bits wide. So you can imagine 8 parallel lines wide. And that's why this device is called an 8-bit microcontroller. Its data bus is 18 bits wide. The other types of microcontrollers, like the microchip PICs, are also 8-bit, or some of them are, not all of them. And the reason is because their data bus is 8 bits wide. And if you'll notice here, you've got PC for port C, port B, and port D. Just like in the schematic for the Uno. We've got these groups of 8 or 6 I/O pins, and the I/O pins are connected through latches. There are like logic gates and stuff that can be controlled. And what the CPU does is it writes a value to this data bus, and it travels all the way around to these I/O pins, and then it controls these lines here to put those 8 bits of data onto the latch that drives each of the I/O pins. So in this case, you can write a single byte to an I/O port and have all of the I/O pins change at the same time. And that's what I'm going to show you how to do in the software here. So if we look at the Arduino world here, we use these functions called pinMode and digitalWrite to access individual I/O pins and do what we want to do with them. What this function actually does is it decodes this information here, what pin number you're going to affect and what you want to do to it. It decodes that information, and it simply creates the instructions to write the appropriate bits to the appropriate data port to get the pins to do what you want them to do. Now, that's possible in the Arduino software. Now, there are some variables or some constants, I should say, that have already been defined for you, and I'll show you one here. And one of them is called port D. And what this does is it defines the I/O port. Just find it here again, the I/O port D. Oops, wrong device here. Let me get back to the ATMEGA. Here it goes. So port D. So what that variable does is allows you to write a byte to port D. It looks like a byte, and in your software you can just say port D equals sign is assigned the value of, that's what an equal sign means, some value, and then what will happen is the microcontroller will write that value to port D. And what I've done here in this example software, I've just defined it as digit port. And I'm going back to the software that I wrote for the digital voltmeter tutorial, and I'll keep referring to that in this. You can see the symbolic constants I defined here. Well, I've just done another one here with port D. And so how do you actually use the port D? Well, like I just said, you make it equal something. Let's get down to the code here. There we go. So remember, digit port was defined as port D, and you use the assignment operator and then some variable or some constant you assign to it. I'll explain how this works. Now I'll go back up again to the symbolic definitions of the symbolic constants of my segment drivers for the 7-segment display. So A seg through to G seg is 0 through 6, and 7 for the decimal point pin. And that's how I wired up my display to the Arduino, was using these pins here. And I chose those particular pins in that particular order for a reason. And when we look at the schematic of the Arduino and the schematic for the microcontroller here, and you'll see the pin numbers are 0 through 7. It also lines up with port D 0 through 7. And so I chose this port to be my segment driver port. Now I've got, I forget which other ports I used. I think it was port C pins that I used. I'm not sure. Well, maybe it was port B. Anyways, I used 4 other pins somewhere else on the microcontroller to drive the digit drivers. But these are the segment drivers, and that way I could write out with 1 byte to that port 7, or port D, sorry, and change all of the segment drivers in one instruction. The way I'd shown you in my Arduino code is that you had to call digitalWrite 7 times in order to create the right combination of highs and lows on that port, in order to drive the display segments to make a digit that you wanted to display. I'm going to show you how to do it in a much simpler way, but it's more advanced, and it requires a bit of understanding as well. So you remember in my description of the software, I created this array of bytes, display digit, and I told the compiler to set aside 4 of them, and I assigned them all 0. I could put any number in here if I wanted to. So if I go back to this other copy of the software that I have, what I've done here is I've created another array, a char array, but a car array. A car is still a byte, it's still the same size. And I told the compiler to put aside 16 of them, 16 bytes, and I initialized them here. And I did it in a binary method, so I set each of the ones and zeros on this port, or on this byte, by using this 0B followed by the 8 bits that you want them to be. And you can see the comment here, the label amp above, I've got A, B, C, D, E, F, G, and then P. Well, those stand for the segment drivers. Remember that segment A was on the port 0, or the pin 0, B was on pin 1, etc., etc. Well, that's how the digits are numbered as well in this 8-bit byte. So this is bit 0, bit 1, 2, 3, 4, 5, all the way up to 7. And these correspond to the same pins on the I/O port. So what I've done here is I've created an array that goes in order of different. So this is digit 1, or digit 0, this is the digit 1, 2, 3, 4, all the way up to 9, and then I added some different ones here, A, B, C, D, E, and F. I just put that in for another purpose. We're only interested in the first 10 here, 0 through 9. And so what I've done here is I've set the 1s and 0s in the appropriate places in order to create a 0 digit, for example. So that means that all of the segments are on, which is low in this case, except for the G segment. Remember, the The G segment is the horizontal segment in the 7 segments that make up a character. And I did that through all of these, all the way to 9 here. And then what I did for the last 6 here is I just created I just made them all 1s, so that if they were output to the segment port, the digit would be blank, as I want to use that. So I've got a character table that's already defined. It's a constant, so I can't write to it. I can't change it. The software or the compiler won't let me do that, but I can access it. So if I put in my char table the index of 0, I get the data for the 0 digit out. If I put an index of 1, I get the data for the 1 digit. And the same all the way down to, if I put a 9 in here, I would get the data to create a 9 digit. And if I take that particular byte and output it to the port D, or the digit port as I've called it, that would turn on and off the different I/O pins in order to create that segment. So how do I use this char table? Well, it's the same way as I use display digits. Like I said, I have a variable that I put into the index, and that's how I index the different bytes that I want to use. So down here, what I've done is now this is going to write, this statement here is going to write one of those digits out to the port D. And if you remember from my tutorial on the software, display digits is another array, and we're indexing it the same way as we do an array. In this case, we're looking at the first digit, and whatever value is in that first entry, first item of the display digit array, becomes the index for char table, and therefore it will pick one of these 9 or 10 bytes and then assign it to digit port. Now I'm going to interject a little mini tutorial here, a tutorial within a tutorial on character arrays, because I think it was pretty advanced what I did here with the char table indexed by another array indexed by a number. So I'm going to just talk quickly about arrays, character arrays or whatever, and how to actually use them and make it a little clearer for you. And yeah, I chose a rather difficult one as an example here because I've got a character array within or an array within another array. So let's kill all this stuff here. Let's look at what we've got here. We've got I'm just going to redo these here. What was it called? Digit. What did I call it? Or display digit. That's what it was. And it was defined with 4 bytes. And I'm not going to initialize it, but I'm going to redo the definition for the make this one 16. Alright, so I've defined these 2 arrays, and I ended up in using this array as an index for this array. A bit confusing, I think. So first of all, to use an array to get something out of it, and we'll go like this, port D is assigned the value of display digit of, and then I'll put an index of 0 in here just to fill in the space. Now the index can be a constant like this. It could be a symbolic constant like from a define statement. Let's call it index just for the hell of it, and 0, and I could put in here like that. And that does the same thing, it just substitutes the 0 in here. I could create another variable let's just assign a number to it, and I could also put a variable in here. Now the compiler knows the difference between putting this word in there and this word in there. So what it's going to do in this case is it'll look at the location that variable points to, the memory location in RAM that variable points to, extract the data out of that byte and use it as the index for this array. In this case, if I put index in there instead of variable, the compiler will simply substitute 0 for index, and that'll become the index for display digit. But you could use a variable, as I've done here, and have the software affect that variable, and that way you have a way of accessing that array dynamically while the software is running, as the software is changing. So you put a variable in there, and that's the case here with this program. So because we're always changing what digit we're going to display, and we are probably changing what digit we're actually displaying in that particular digit, so I've made this array dynamic, so it can change with the software. So again, I can use potd. Let's get it spelt right here. I can do it again. I'll use the char table, just like I did in the, and then our index. Oops, wrong. So again, I could put in here a constant. If I put 6 in there, I'll get the data out that will make a 6 on the display. But I can use the display digit as the variable. Because remember, display digit is simply 4 bytes in memory. They're just 4 variables stuck together, and they're accessed together. They're created as, or considered as one object. Then you can get each piece of it out by simply indexing which object you want by putting that in the square brackets. So if I wanted to, let's see, let's do this. If we're looking at display digit 0, and we want to display the character that's in display digit 0, so I can simply put that as the variable in here. So it is confusing because you've got an array within an array, but just think of this as a variable. Remember, it's just a byte. It's given the same name as the other 3 bytes in the array, and to identify the different bytes, you have to just put this index in here. So what we're getting to is whatever the contents of display digit 0 is used as the index to char table to get that character out. I hope that you can understand this. It took me a while to figure this out too, but just remember that the index in an array can be a constant like this, it can be a symbolic constant like this, or it can be a variable. It doesn't matter. The beauty of being a variable, of course, is it allows the software to dynamically change what item in the array you're actually indexing. So back to the regular tutorial here. So this makes it a much simpler way of outputting data to that port. Now, of course, we have to write to that port in such a way initially to either make all the pins inputs or outputs. And going back to our ATMEGA schematic here, or a data sheet, and let's look at I/O ports. So here's a very rough schematic of what one I/O port looks like. There's some logic here that drives it. Be the 2 transistors, one transistor high and one transistor low on the pin, just like I talked about in one of my earlier tutorials. And this is actually the pin on the microcontroller. The rest of this stuff is actually inside it. And you'll see there's a couple of diodes here. These are static discharge protection diodes that help to make the device more robust, so that if you zap this with some static, it's not going to the voltage isn't going to get inside and destroy some of the logic and make the microcontroller unable to use. Now, with each I/O port, there are actually 3 different registers on an ATMEGA, and one of them is called port, and I used that already, port D. And there's another one called the data direction register, which is the one we're looking at right now. How do we determine which pin is an input and which pin is an output? Well, the data direction register, or DDR, as it shows here, if you write to that with the combination of 1s and 0s, that will set the I/O pins to be their inputs or outputs. So any pin that is written a 0, that makes it an input. Any pin that's written a 1 will make it an output. So in my case, for port D, because I want to make them all outputs, I wrote all 1s to those initially. Or I actually didn't do that in my software. I used the pinMode, but you could also do that to simplify your software. The third register is called pin, P-I-N-D in this case, for pin, for the D port. And that, if you read that register, I'll have to show you some code how to do that in a later tutorial, but if you read that register, it will give you the state of the I/O pins, whether they're pulled high or pulled low by something driving those pins from outside the microcontroller. Now I'm going to look at another microcontroller. Arduinos aren't the only thing out there. I'm sure you've probably heard of others, but I'm going to look at the MicroChip PIC, which is also a very popular microcontroller. And so this is the block diagram of the inner workings of the MicroChip PIC. It looks more complicated than the ATMEGA, but it's not really any more complicated. It's just the way that this drawing has been done. It shows a lot more detail. But if you look here, you'll see again an 8-bit data bus that travels all the way around the whole device, all the way around to every peripheral that's inside it. And these are the I/O pin ports as well. So if you count them, there'll be 8 bits on each of these ports. So the I/O pins are set up in the same manner with the MicroChip PIC controllers. They only have 2. Oh no, they have 3 registers as well. So they've called them. They've got, of course, given them different names. But the trice register, you write to that register to tell which pin is going to be an input and which pin is going to be an output. And in this case, with MicroChip, it's backwards. If you want a pin to be an output, you write a 0 to it. If you want it to be an input, you write a 1 to it. The port register, if you read that port, it's a little different and it's a bit confusing from the ATMEGA because the port registers, same name, but they do different things here. In this case, with the MicroChip part, the port register, you read that to get the data that's on the pins. And then the latch register is what you actually write to in order to put the data out onto the pins on that particular port. And their ports are port A, B, C, D, and E, depending on how big the device is. I'm not sure where the port numbering system for the ATMEGA came from, because they give them a different numbering. Some of them are kind of missing out of the sequence. There's no port, I don't know, where are they? There's no port A actually. I guess that's the one that's missing. But in the MicroChip part, they just start with A and they go up from there. So you can see that this is very similar to how the ATMEGA works as well. So they work pretty much the same way. There's slightly different ways in the definitions, but if you look at any microcontroller, in fact any kind of microprocessor or CPU type device, this is how it's done in them. Some of the more, like the Intel devices used in your PC, they're much more complex than this, but the same basic idea is used. You can assign the pins to be an input or an output by much the same method. Just on an Intel device, the data bus is 64 bits wide, and there's a whole lot more going on inside them. Oh, I know one thing I didn't show you. Let's show you how to read a pin. So let's say I decide to define one of my, or make a definition here, like a define statement. What do I call it? In port, and I want to read what's on port D. Oops, I have to go PIND, like that. And I want to read it, so I've got another variable, say it's byte. For lack of imagination here, I'll call it data. And I want to get the value of what the pins are on port D. I will simply go data is assigned the value of in port. And that's how you read an I/O port. I could do the same way here. To assign the value, I could just use PIND. Remember, as I said earlier, these are already defined. And there's a description in the Arduino reference guide on how to directly access the I/O ports as well. And I'll put a link into that at the bottom of the video here. So another advanced programming technique for you to try out. It's certainly a much faster way of accessing the I/O pins on your microcontroller, because you can write a whole byte at the same time. Actually, I'm going to keep going here. Let's say I want to write something to the port D, but I only want to change one bit, for example. This is a way to write to the whole port with one, but only write to one bit at a time. Let's see, say I want to put a 1 on the third pin, so that would be pin 2. So I can do this statement here. It's assign the value of port. Well, let's do it this way. I can write it directly out using the 0B, the binary method. So 4, 5, 6, 7, 8. I put in all of the bytes or the bits first, and then I go modify what I need. So I said the third bit, so I can do that. So if I wanted to write a 1 to the third bit only on that port, I could do it that way. Or the thing is that it will affect all of the pins on that port at the same time. And say you've got other stuff being driven by this pin here that you don't want to change. You don't want to make it a 1 or a 0 in this case, but because the software is running, you don't know what the value of this pin should be at the time that you're going to write to just this pin here. There's another way of doing it. You can OR in that pin if you want to set it to a 1. So I'll do it again. Port D is given the value of port D. I want to set it high, so I'll OR it, and this is the, if I can find it on the keyboard here, that's the OR symbol. 0 B 1, 2, 3, 4, 5, 6, 7, 8. Go back to this one here. Boom. So what that'll do here is it takes a copy of whatever is on the port at the time, and then it just simply puts this bit as a 1, sets this bit as a 1. If for some reason I wanted to make that same pin 0, I would have to AND in a 0. So I'll do it again. Port D is given the value of port D and, where's the AND? This time it will be 0B, 1, 1, 1, 1, 1, and a 0 there, and the rest are 1s. A bit confusing, but that's how you can write a single bit at a time. Now in the native code that the microcontroller understands, there are functions, or there are instructions that will set or clear a single bit on a port, and that's one instruction. So the compiler generally is smart enough to know that there's only one bit being changed here, so it's going to change this whole C statement into one single assembly instruction that the microcontroller can understand. If I needed to affect more than one bit here, but not all of them, I could just write those myself like that, and that would do the same thing. Same with over here. I can make that a 0. Now in this case the compiler won't create a single instruction. It will probably do this, it'll actually take a copy of port D and in this, logically and this value in with it, and then write it back out to the port. It takes a few more instructions to do that, but it's still a lot quicker than a pinMode or the digitalWrite instruction. So very quick tutorial on some more advanced software techniques. Again, I will put a link down below here for the section on I/O ports that's in the Arduino reference guide. It's quite clear on how to use it. And these constants here, pin D and port D, same with port C, port B, and pin C and pin D, etc., etc. Those are all native to the compiler. They're already defined for you. You don't have to include them anywhere. You don't have to create them yourself. They're already given. So, I hope you understood this, and I hope you enjoyed this. And I'm going to keep going with this kind of under the hood type of look at how the microcontroller works. I'm going to probably use the Arduino, the ATMEGA, as the main example, but I will flip back and forth between MicroChip PIC and the ATMEGA. I'm very familiar with both of those microcontrollers because I've done quite a few designs using both of them over the years. And so I'll start digging deeper into the inner workings of these devices to give you a better understanding of what's going on. What Arduino is doing by creating these functions, pinWrite or pinMode and digitalWrite, digitalRead, etc., etc., they're taking away from this more complicated way of working with the microcontroller and simplifying it. And that's great. It's a good way for people to get started in this. But if you really want to get into this more deeply and get kind of really good with your code, you need to start digging deeper and start not using some of those built-in functions with Arduino. And what you'll find is that when you compile those functions, you start using up a lot of memory. They do use quite a bit of code. And by doing it this way instead, you use up a lot less code and you'll be able to put a bigger project into your microcontroller. So anyways, long-winded as usual. I hope you enjoyed this. And please stick around and watch the next one. I think I got something kind of cool in mind coming up. Take care. Thanks for watching.